Okay, so we will now talk about section 3.2, the orthogonal expansion. So let's see. We will actually learn about one type of expansion we call Taylor expansion. Of a function. So for a function fx, certain function fx, we can expand it as a Taylor series. Let me just, for simplicity, just write as a Maclaurin series. The center is at 0. So we have this Taylor series. This is a0 plus a1x plus a2x squared plus an xn, and so this series may converges to this fx as now. What the idea here, this an are Taylor coefficients are determined by this nth order derivative at the point 0 over n factorial. So one example that we have is e to the x equals to 1 plus x squared 2 factorial plus xn n factorial. So this is the Taylor expansion. This is the Taylor expansion of the exponential function. Now, the idea of this is that, okay, we expand an arbitrary function fx in using these monomials. This is like 1. So that is, we expand everything as an infinite sum with constant coefficients involving this in terms of this system. So this is the essence of Taylor expansion. Now we know that Taylor expansion, if we look at this first n term here, actually n plus 1 term, this is the Taylor polynomial of degree n. So this would be a good approximation of this when x is near 0. However, when x is away from 0, this may not be a good approximation for a given n. Let me say this given n. For example, when n is 1, the Taylor this actually is just the tangent line. So tangent line, the approximation, okay, this point is A. When x is close to A, then this is a good approximation. This is a good approximation. Tangent line is a good approximation of this curve. But when x is away, like in here, then this is not a good approximation. So that is the disadvantage of Taylor expansion. Now, if we come back to look at what we talked about in the last section, we have an expansion. We expand an fx in terms of a1 sine x plus a2 sine 2x and an sine n. Let me change this to capital N, so that capital Nx and n. So now a function now is now expressed as an infinite series of sine functions. Now in this case, the basic elements here are those trig functions. So that our system, we express every function as a linear combination, an infinite linear combination, infinite sum of of these functions. Now, so this kind of expansion is what we call as a Fourier expansion, or Fourier series expansion, we would call. And then because later on we will talk about Fourier series that involve both a science function and cosine function, but here we have only science function, so this we call it Fourier sine series, or Fourier science expansion for fx over the interval from 0 to pi. So that is now if we look at the first n terms, so we call this as the sum of first n terms. One of the fundamental difference is that this approximation actually we use the as n to approximate this is actually would actually be good approximation for all holds in general, is a global approximation, or for all x in from 0 to pi. Now let's look at how do we have these come back to look at how these Fourier science expansion or Fourier science series and from 1 to infinity. Now the key fact of this is that these functions let's call this as fn x. These are our basic functions fn, and so we write it as an fn x n from 1 to infinity. Then the basic we determined last time we said that this an is given by 2 over pi from 0 to pi fx sine nx dx. Now that is this is we write as fn x, and this is 2 over pi 0 pi fx fn x dx. So this is the integral of the product of this function against the basic functions. Now the key fact in arriving at this formula is the fact that this integral for sine nx sine mx dx is 0 when n is not m. So that would be if we use this notation, this would be fn x fm x dx is 0 when n is not m. Now this fact here, we said that this is saying that fn is orthogonal to fm. Why is that? That is because on these functions, for this function, we introduce an inner product. And then this inner product is defined as fn, the inner products of fn and fm. We are, if you remember what you learned in linear algebra, two vector in a inner product space is perpendicular or orthogonal if and only if the inner product is 0. Okay, so now let me recall the concept of inner products. So now we have a vector space. Now this our vector space is, or what we call as L2. L here actually stands for Lebesgue, but we're not going to talk about Lebesgue integral here. So these L two functions are the what we call as the square a family of square integrable functions on AB. Specifically, it is that when you square this function and you calculate integral from A to B, and this integral should be finite. So that is the concept. Now you can see that this actually is a vector space. The vectors is actually functions here, are functions that satisfy this condition. Now this space also actually you can define an inner. This is called the L2 norm square. So you can define an inner product on this space. The inner product is defined if you have two functions or two vectors, and then the inner product is defined as the integral of their product. Now recall, what do we mean by inner product? Inner product is a product defined on a vector space that satisfy it must be linear. So which means that if you have C1F AX plus BGH, this equals to AFH plus BGH, and then it is symmetric. Symmetry, that means that if you interchange F and G, the product should be the same. And it has the satisfy the positivity condition. That means that in the product of F with itself, it is always non-negative, and the inner product of vector with itself is 0 if and only if F is 0. Okay. Now the L2, this L2 space, the family of square integrable functions with this inner product is now become an inner product space. So for an inner product space, you can define the norm, which actually is consistent with what we have here. The norm is just the square root of the inner product of the function with itself, so that these two formulas are consistent. You take the square root to both sides of this, then you get this. So that is this space of function become an inner product space once we introduce this inner product. For any inner product space, we can remember we can define the angles of two vectors. The angle between two vectors F and G, if you remember, is the inner product of F and G over the norm of F times the norm of G. And so therefore this is orthogonal if and only if the angle is pi half, which is means that cosine of pi half is 0. So that means that F and G is 0. So that is where this orthogonality, the concept of orthogonal comes about. So times tgx dx equals to 0. All right. Now we have so we are given this fn. Let's come back to this the case when we look at the space of 0 pi, and we are given these functions sine x and sine nx. So this is a system of fx, f1. This is fn. Now this system, infinite system, f1 x fn x is okay. This is also true. A general concept. Yeah, this actually is infinite, so it also have terms. This is orthogonal. That would mean that f n and fm, the inner product, each two vectors are orthogonal to each other. So that means that their inner product is 0 when n is not the same as m. Now, the norm of these vectors is fn square is fn. So that means that when n is m, then this is the norm square. So if furthermore this norm is 1, then we say that fn, this where n runs from 1 to infinity, is orthonormal. So normal here just means that the norm is 1. It's normalized. The norm is 1. So in this specific example here, we see that if fn x equals to sine nx, this system here n from 1 to infinity is an orthogonal system. So it's a infinite sequence of functions where each two distinct functions are orthogonal to each other. So it's an orthogonal system. Now, the norm of these is fn, the norm of this, which is this, is the indigo. Let's look at the norm. The norm is the 0 to pi sine square n x dx. We did the computation before. We said this is pi half. So this is not 1. So therefore, this is not this fn x n from 1 if it is not orthonormal. So because the norm is not 1. But we can, if we divide both sides by pi 2 over pi, so then we have this equals to 1. Then we move this inside the norm, so this would be square root of 2 pi fn. This equals to 1. So if we let this gn x equals to square root of 2 over pi fn x, which is square root of 2 over pi sine nx, then this sequence, this system here is 2 over pi sine nx, n from 1 to infinity, is an orthonormal system. So this process that is what we call is normalization. So you just divide both side by constant, and then you get orthonormal system. Okay, so let's look at another example of how to calculate the inner product of two functions. Let's say we have fx equals to x cubed, and then gx equals to 1 plus x. Those are the functions we consider as functions on the interval from 0 to 1. So these are the functions in this L2 space. Now, on this L2 space, there's inner product. So let's see whether how do we calculate the inner product. It's just the integral from 0 to 1 of f x times gx. Now this is easy. This 0, 1, x cubed 1 plus x dx. So therefore it is 0, 1 x cubed plus x4 dx. So it's 1 4 plus 1 5. So it's 9 over 20. So this is not 0. So f and g are not orthogonal to each other. On the other hand, you can also calculate the norm of f. What is the norm of f? The norm square of f is the integral. Okay, let me just slow down a little bit. So this is just the inner product of f with itself. So that is the integral from 0 to 1. F times f is just x to the 6 dx. So it's 1 over 7. So the norm actually is the square root. You take square root to both sides. 1 over square root of 7. So that is this example. Now, the Fourier, the idea of Fourier series is a method is that for given function fx, we like to express this as an infinite sum with coefficient to be determined of this. We assume that fn is an orthogonal system. So we like to express this and this. Fx as an infinite sum with, on these basic elements. Now, when you talk about an infinite series, you need to be careful. You need to discuss the convergence. So what does it mean by convergence? So that is, you look at you replace the infinity by a finite number. In finite sum, you can always compute a finite sum, and then you take the limit as n goes to infinity. So this term, the finite sum term, we will call it as x capital N x. So there's a sum of is a partial sum of the first capital N terms. So now in here, the convergence actually we can discuss in three different ways of convergence. In three different ways. The first way is the way that we are familiar with, is what we call is a point-wise convergence. That is that if you look at xn, x, and fx, then this term, the limit of this term, as capital N goes to infinity, goes to 0 for any x in AB. So that is point-wise convergence. For any point, this xn converges to f. Another sense of convergent is what we refer as the mean square convergence. The mean square convergence is that we look at the L2 norm of the difference between the finite sum, and this is I take that, so this is the integral between AB of Sn x minus fx square dx, and this is 1/2, and this number goes to 0 as n goes to infinity. So that is or if you square to both sides, that is that this integral as n goes to infinity, this integral as n x minus fx dx, this term goes to 0. Another sense of another way of convergence is what we usually refer as norm convergence, or the uniform convergence. Uniform convergence is that, okay, instead of looking at this, we look at the maximum of this. Maximum of this for x between A and B, assume the maximum, and this maximum goes to 0 as n goes to infinity. So this is usually referred as the uniform convergence. We are going to be focused on the mean square convergence and point-wise convergence, but let me just make a remark that in general, the uniform convergence is stronger, implies the point-wise convergence. It also implies the mean square convergence. Mean square convergence. Okay. All right. So let's look at an example here. Example 2, not example 3 already. We have this infinite series from 0 to infinity, -1 n x 2n, and we said that these converges to 1 over x squared point y, and also mean square, this but not uniformly but not uniformly over the interval from -1 to 1 over, the open interval, from -1 to 1. Okay, how do we do that? How do we show that? So when we talk about conversion, it means that the finite sum, which is from 0 to capital N, -1 n, x to n, this converges to this function of 1 over x squared. Now this finite sum, if you look at it carefully, it actually is a geometric series with common ratio -x squared, because it can be written in this way. Now this actually, the sum actually is not from, is not going to infinity. The sum is from 0 to capital N. So therefore it is 1 minus -x squared to n plus 1 over 1 minus x squared. Now, when for any x that is between -1 and 1, we know that this term here would go to 0. So therefore, the limit, since n plus 1 goes to 0, so we know that the limit of Sn x minus 1 plus x squared as n goes to infinity is, this would be x2 square n plus 1 over 1 plus x squared. As n goes to infinity, of course, this is 0. So therefore, we have point-wise conversions. By the way, some of you may have learned this kind of concept in Advanced Calculus 1. And if we look at the indigo, let me change color. If we look at the norm between x n minus this function, norm square, that is this indigo from 0, -1 to 1 of, so xn minus this is, as we had here, is, and then we square this, so it's x square n plus 1 square and 1 plus x square dx. Now this denominator is always greater than 1, so therefore this term is always less than -1 to 1. X, this becomes 4n plus 1 dx, and then you integrate this. This is, this would be 4n plus 4 plus 1, so 4n plus 5, and 1 minus 1, -1, is 2, so you get 2. Of course, this term goes to 0, as n goes to infinity. So this implies that this series converges to this function here in mean square norms. So it's mean square convergence. However, we do not have the uniform convergence. Is because if you look at the maximum of as n x minus fx, so x is running from -1 to 1, and this is the maximum of x 2n plus 1. We have this expression before. Now x run from -1 to 1. Now as x become close to 1, so we know that this would be greater or equal to when x is 1. So it's 1/2. So therefore, this would never approaches to 0 as n goes to infinity. So that what this tells us is that we have no uniform convergence. So actually, I should make a remark that this max here actually is better to use as the soup. Actually, is what we call is the least upper bound. Least upper bound. Okay, so but I don't want to make this a fuss about this. All right, now let's come back to the Fourier series, and then the generalized Fourier series. Now, the main theorem that we have here is this. So this is the generalized Fourier series. Suppose we have fn is n runs from 1 to infinity, is an orthogonal system then and suppose suppose fx equals to an fnx n from 1 to infinity, where the convergence here is mean square. So it's in the way of mean square that we just talked about. Then this an is given by the norm of fn square and f, the inner product of f and fn. This is the first part, and the theorem, and furthermore, the norm square, to look at this from infinite series, and then times the norm of fn. Let me see. I should have this is I should not have a square here. Okay, I would now come back to see this point a little bit later. So, and the norm, this Fn is norm. Okay, this and this norm here is square. So the coefficient is given if we have this is square. So this I'm now trying to have this. So this would be an square, and this would be Fn. So this, okay, would be less or equals to F norm square. Okay. All right, we will come back. In particular, if Fn is normalized, that means its norm is 1, then we have this inequality which we would call, which is called the Basel's inequality. Okay, so I would just keep a proof of this, but actually is a heuristic proof of this. Now, okay, how do we determine these coefficients? You have F equals to an Fn, n from 1 to infinity. You find the inner product of F with Fm, and then this is n from 1 to infinity, an F n Fm. But we know that this is orthogonal, so that means that if n is not m, then it would be 0. So the only term that's not 0 is when n is m. So that in this case, this is Fm. So, but this is am Fm square. Okay, so therefore an is determined by Fm square, F inner product to Fm. So what I wrote down here, actually, I should have a square here, so that is consistent with my formula here. But okay, so now, how about the Parseval's theorem? I would actually do. If you look at F, the inner product, so then that would mean that you have an Fn, and this sum here is, I will write am Fm. This is a dummy variable. I can change to whatever I want. Now, these terms Fn and Fm would be the inner product between them would be 0. So this is sum n from 1 to infinity, the sum m from 1 to infinity, an am Fn Fm. Now, these term here would be 0 if n is not m, and it would be n is m, it would be just the norm of Fn. square. So what I have here is an square fn square n from 1 to infinity, and this left hand side is the norm of this. Actually, I put an equality rather than inequality. The reason is that I assume that this actually equals to this. So this equality is, we will later say, is a Parseval equality. Equality. All right, so that is a kind of like a sketch of the proof, but actually it's not a rigorous proof. But here I also need to come back to modify that. I should have a square here. All right, now so this actually in this proof, we actually assume that f equals a function can be expressed as the infinite sum of these but this, as I said, is not true always. But then we have this new definition. We said that fn n from 1 to infinity is a complete, so this is a complete orthogonal system if any f in L2 AV, we have the Parseval's equality. We have the norm of this is an square fn square n from 1 to infinity for any where this an is what we call as the Fourier coefficients of these Fourier coefficients. All right, so that is the concept of complete orthogonal basis, and the theorem is that of course theorem 2 is that fn n is from 1 to infinity is complete. I would say is orthonormal. So that would mean that these norms would all be 1. Then if and only if for any f in the L2 space, the complete the square integrable functions fx can have a Fourier series expansion. With respect to the spaces where these an are given by the inner product of f and fn. So these are Fourier coefficients. This is generalized Fourier series. And this is a Fourier coefficients. So that is the theorem. Now, so this convergence means that if you look at the finite sum, of n term. So this is a n f n x. The sum is from 1 to capital N. This limit here. So this is the Sn. Now this conversion here is mean the conversion is mean square. What it means is that Sn x minus fx square of this, which is the norm of Sn x minus fx, the integral from from A to B is 0. We have a square here as n goes to infinity. Now, another theorem I actually am not going to prove is is called the best mean square approximation theorem. Which tells us that the norm for any okay, let's given an orthonormal system requires Fn from 1 to infinity, then you look at the norm between, you approximate this by this Fourier finite sum of the Fourier series actually is the best among all the f if these are all in mean square norm of OG for any G that is a linear combination of Fn x Cn, this n from 1 to n. That is, this linear combination sometimes we said that this is in the span of the functions of f1 up to after capital N. Okay, so that is, again, I'm not going to prove this, but instead I'm going to look at an example. This would be my fifth example, I believe. So I ask you to find Fourier sine series for fx equals to x over the interval from 0 to pi. Okay, now just have it simple, just have this equals to 1. Now, this you can do the computation. So you have fx, which you write as an sine nx. We know that this is an orthonormal system, orthogonal system over L to 0 pi. And then the coefficients an is given by then by the norm of let's write this as fn x square over the integral from 0 to pi of f inner product to f in this case is 1 inner product to sine nx dx. Now this norm we already compute. This norm is fn square is the integral from 0 to pi of sine square nx. If you remember that this is pi half, so therefore the reciprocal of this is 2 the reciprocal of this is 2 pi, and this integral of course is negative sine negative cosine nx over n, the integral from 0 to pi. Now when n is even, when n is odd, let's see, even first, then this would be a two integer, you have kind of like 2 pi minus cosine 2 pi minus cosine 0. Therefore this term would be 0. So this would be 0. When n is odd, and then you would have a negative 1 minus negative 1, so it becomes 2, so it becomes 4 pi. So therefore the Taylor, the Fourier series for 1 is this. You have only you have only the odd integer terms, so it's or pi 4, but you have sine x plus sine 3x, or the odd integers. This is the Fourier expansion, science series expansion for 1. Now, if you remember, we have these Basel's inequality, or Pascal's equality, that would have that an square fn square equals to a norm of f. Here is from 0 to pi. F is 1, so this is pi, and this is n from 0 1 to infinity. So these an's are this is 1 over n here. I should have this is 1, this is 3. So what this tells us is that we have I have all those coefficients. The square of this is 16 pi square 1 over 1 square 1 over 3 square, and then this times the norm of all of these are pi half square, and this equals to pi. So therefore, let's after cancel things out, we get to this formula of 1 square plus 3 square plus 5 square. This equals to pi over 4. So we have this interesting identity that comes from that express pi as an infinite series. So That is what I'm going to talk about today.